Hi, everyone. Thanks for coming. Really good to see you all. Yeah, I'm Peter Cook, and I'm going to be talking about particle flow animations. So I've got some. If you are, I don't think any of you absolutely don't need to, but if anyone was wanting to kind of look at the code or stuff on their laptop, I've tweeted out on, sorry. Yeah, my Twitter is Peter_R_Cook. So I've tweeted out the repo with the code samples and the slides as well. So yeah, or you can look at them later. So quick little bit about me. So I've got a maths and engineering background. I spent 10 years writing computer-aided design software, and then a few years as a freelance data viz designer and developer. I'm currently part-time visualization developer at a company called Flourish, who do kind of visualizations as a kind of SaaS service. I've written a book, D3 Start to Finish, and a course, Visualizing Data with JavaScript. I'll give you just a very quick plug on that. So the course just shows you how to build various things with JavaScript, like bar charts and maps. There's a D3 visualization in there, how to make a data story, and like a dashboard, a simple dashboard as well. So if you're interested in that, you can check it out at createwithdata.com. I've got various websites down here as well. Okay, so I'm here to show you how these, has anyone seen, prior to finding out about this talk, has anyone seen these maps with the kind of flowy animations? I don't really have a sense of how well known they are. So a few of you. So I'm going to show you how these kind of maps are created. So you've got a really nice sort of animation showing wind speed and direction. So I first saw this map around the time it was launched in around 2012. There's kind of a lot of activity in the sort of data viz space around that time, I think because of a lot of the web technologies that were becoming available at that time. And I was just really sort of impressed by it. I think partly just because of it looks really good. It's also effective because it kind of instantly gives you a sort of a visualization of wind speed and what the wind is doing. But I think from a technical perspective, I was just fascinated. How did they do that? And I had no idea at all. It's quite interesting. I mean, so this was created by Fernando Viegas and Martin Wattenberg in 2012. And actually, the sort of basic idea behind it actually sort of dates back a long way. I mean, you could take it back all the way to sort of the 1600s with, I think that was Edmund Halley, who kind of had the idea of representing kind of flow using these little particles. But certainly in the 80s, people were kind of actually animating them. But I think it wasn't really until this one that this team actually made it as a web piece. And then a couple of years later, someone else kind of took that idea and kind of really ran with it. They added color to it, but also made it more of a sort of 3D type globe, so you can actually kind of rotate it and zoom in. And it's the whole world rather than just the United States. There's different layers that you can view on it as well. And so this is created by Cameron Beccario, and this is an open source project. There's a really great talk on it where he kind of gives you the story behind it. It's really worth watching, but I think, initially he didn't have a job. Says he's collecting stamps and just needed a new project. And so, he decided to build this thing. And it's a really impressive piece of work. I think it's also impressive because that's done, 10 years ago, and it kind of hasn't really fundamentally changed in all that time. And yet it still looks amazing, works well. And I think he's still adding bits to it, such as there's different layers like ocean currents. There's a mode for that. Different projections as well, some crazy projections in there. So yeah, I think kind of being an engineer, I was thinking, well, how do they make these things? I had a sort of first attempt around that time, but I just didn't really have a clue of how to do it. So I kind of sort of guessed my way through it and used SVG. I used D3 to kind of animate the length of a line. And also, I think attaining the data was a bit of an issue for me as well. So I kind of found Met Office data, but it wasn't grid-based. So I kind of wrote this script to sort of distribute the points kind of by hand. So that was kind of took longer than the actual writing the map. But yeah, it's okay, but it isn't quite what, wasn't quite the same. And also being SVG, it's a lot slower, so you couldn't have so many points at a time. And then, yeah, I had another delve into it more recently. And you can actually also, actually delve into the code. So in the case of the Earth one, so the 3D one, I managed to find where kind of the core algorithm is. So I could see. So if you do sort of go on these slides, you can kind of click through to the actual source file. But you can kind of see there's some kind of iteration through particles. So I guess particles is an array, and then for each particle, it's picking out the position, and then here we go, vector at current position. So I guess that's at the current position, that's the direction of the wind, I guess. And then it seems to be adding something onto that position. Okay, so we've kind of found the code there. And then, yeah, the actual drawing of it, something interesting going on here. Every time it draws it, it's drawing a rectangle the size of the canvas, I guess, to clear it. And then, yeah, it's actually drawing a line for each particle. And this is in the first wind map, so the one by Viegas and Wattenberg. And we see some fairly similar code. So there's a method called move things, iterating through particles, and then kind of adding some kind of vector onto the position of the point. You can actually, I mean, it's pretty old school, this. There seems to be just a single script, which is probably just handwritten, so no build tools, which is really nice to see, back in 2012. So the entire code is here, including kind of hard-coded data as well. But there's a nice comment in there at one point saying, please don't hate on this code too much. It's late and I'm tired. So yeah, it's really nice just being able to kind of open that and see the code. So before I start looking at how this is made, I've just got a few definitions here. So particle, just to define what I mean by a particle, it's just a single point located in sort of a two-dimensional space. So it's kind of just an X and Y coordinate. So in this case, we've got something located at 10,50. So 10 is the distance in the X direction and 50 in the Y direction. So that's a particle or a point. A vector is an object with magnitude and direction. So think of it as an arrow, but also the length of, well, the arrow direction defines the direction, but the length of the arrow is important as well. That defines how the sort of the size of the vector. And down the line, we'll see that kind of defines the speed of a particle. And also a vector doesn't have a position, it's just a direction and a length. And then velocity, so that it's also a vector, but it's kind of a specific vector that defines a particle's travel direction and speed. So as a little example, we've got if the velocity is this, which is 40 in the x direction and 30 in the y direction, then 40 is like, it could be anything, it could be like 40 pixels per second type thing. And so that means that if you've got a particle here, then after 1 second, it's going to be 40 across and 30 up. And then a velocity field is a grid of velocity vectors. So every coordinate across this, let's call it a canvas, has an associated velocity vector. So that's what the field is. I've only drawn, and it could be that you've just got a few vectors like I've drawn here, or they could be defined for every pixel, or we could, yeah, like I say, have a sparser grid, and we could kind of interpolate if we wanted the vector kind of in between where they're already defined. So how would we represent these in JavaScript? So how might we represent a point or a particle in JavaScript? Any ideas? Yeah, cool. Yeah, anything else? I think that is my first one. There we go. There we go, perfect. Likewise, a vector. Length. You could do length and angle, actually. I didn't think of that one. So yeah, it could be length and angle. So the angle is the direction and length is kind of the speed. Yeah, I didn't think of that. Yeah. So remembering it's just a, okay, clue. So it looks like that. Oh, in fact, I've kind of shown it there. So yeah, you can use, it's kind of similar to a point. So again, if you think it's just a direction, so if you kind of imagine it's something that's pointing 40 to the right and 30 up. And likewise, yeah, you can use an array. Velocity is also a vector, so we can use a similar representation. How about a grid or a velocity field, or a kind of a grid of vectors? Dave? Yeah. Array of arrays, yeah. It could, well, yeah, I guess, yeah. Yeah. So here, yeah, so this is what I've used in the example. So it's a 2D array of velocity vectors. You can kind of think of it, unfortunately, the way I've done it, it's not quite like this, but you can almost imagine each of those arrays as a row, and then each object is kind of as you work along. But I've kind of flipped it around, so each top level array is actually a column. And the reason for that is so that you can kind of address, index it like this. So let me try and zoom in a bit. So if field is this 2-dimensional array, you could index it using, so the first index is the X position and the second index is the Y position. So it kind of works quite naturally that way. But yes, yeah, or yeah, there's so many different ways. I mean, you could even define it using a function that takes the X and Y position on the canvas and returns whatever that the vector is. Okay, so here we go. This is the basic process. So first of all, we need a grid of vectors because we need our particles to have, a direction. They need to know what direction they're going to be moving in. And then, yes, we're going to add some particles. We're going to create particles. And if you remember, they're just points. They're just X and Y coordinates. So we're going to create them at random positions. And then for each particle, we're going to move them in the direction of the vector. So if we kind of zoom in a little bit and we've got a particle here, what we want to do is find out what the velocity vector is at that point and basically add that velocity vector to the point. Okay, so that is the basic principle. I think so fundamentally it's actually fairly straightforward, but there are just little tricks that actually make it look really nice, which I'll show you. So to define a velocity field, in the case of the wind maps, I mean, they're working from real data. I kind of looked into where the data was coming from and just got a bit scared of this because I had to sort of install various scripts and I just didn't really want to go down that path. And also, yeah, I thought it'd be nice just to have like a self-contained script that wasn't relying on any external data as well. So rather than doing that, I wrote just a little function that generates a velocity field from what I'm calling seed vectors. So if you imagine you start with these red kind of positions and vectors, I'm using them to define a velocity field. So don't get too sort of hung up on this side of things. All this is doing is creating a velocity field, basically like a two-dimensional array of these velocity vectors. That's all it's doing. So, if you're using real data, you wouldn't need to do this step. And yeah, like I said before, we could, and I can show you examples of this later, we could actually generate a velocity field using a function. So so this is an example where it's using a sine function to kind of generate a generated velocity field. So in the code, I've got various steps. Let's go and see the code now. Actually, let me go. Let's close that. So I've got 6 steps here, which I'm going to go through. So the first step is where we generate the velocity field. So the red seed particles are randomly generated. So if I refresh, it creates new seed particles, and then from that, it creates a velocity field. So this velocity field is where we're going to be kind of moving our particles through that field. Yeah. So that was, so that's step 1. Yeah, so this is where it gets interesting. So now we're going to try and step a particle through the field. And the way in which we'll do that is we'll create one particle. We'll place it in the middle of the canvas. And then we're just going to kind of use a key press to step. So we're not using any kind of animation loops or anything initially. And each time there's a key press, it will read the velocity at the whatever the location of that particle is. So it's using that big array with which we generated back here, this array here called field. And then it's getting the velocity from the field, and then it's adding the velocity to the particle. So it's doing that for the X direction and then the Y direction. and then redraw the particle again. And so if I go to step 2, and so now if I do a key press, you can see it moving through the field. I need to refresh each time it goes off the screen. Okay, and you can kind of see that it's following the direction of the vectors. There we go. Good stuff. And just as a bit of background, it's using the canvas element. Who's familiar with the canvas element or has used it? About half of you. Okay, so in web development, there's, for doing, if you wanted to sort of draw lines and kind of shapes and stuff, there's kind of mainly 2 approaches. There's, you can do it using SVG or using a canvas element. They're kind of similar, but underlying it is quite different. So for SVG, you've still got, you're kind of adding elements to the DOM or the document object model. So it's similar to HTML. So HTML, you've got things like divs and paragraph elements. SVG, you've got line elements, rect elements, there's path elements, there's circle elements. So you're kind of adding those to the SVG element. That's cool because it's great because you can kind of go back and then change something about. So if you've added a circle, you can go back and change the radius, for instance. With the canvas element, once you've drawn something, it's drawn to the page, but you can't then do anything with it. It's kind of just sort of painted on the page and that's it. It isn't added as an element to the page. But what this means is that it's a lot more performant. So it doesn't matter how much painting you do, there's not really going to be any kind of overheads with that. And so that's why this kind of a thing, the canvas element is ideal for this. Well, I suppose there's WebGL as well, but I haven't gone there for this. And it is, I'll show you later, it's quite surprising how performant this actually is. So here so in the HTML, we've got a canvas element. And then in the JavaScript, we need to get hold of what's known as the context. So this bit of code is fairly standard. And then I've got a couple of examples where we set the fill style and then draw a rectangle. So these are the coordinates. I think it's the top left, and then the dimensions of the rectangle. And then to draw a line, there's other ways to draw a line, but this here we're creating a path, and then we're sort of moving around, drawing a line, and then we complete it by calling stroke, which turns it into like an outline rather than a filled shape. So as we saw, when we keep going, the particle just goes off the screen. So that's sort of, the first, but it's maybe something we need to deal with. Anyone got any ideas of what we might do if it goes off the screen? Ali? Yeah. Where would you reinitialize it to? Could do. Any other ideas? Could you do like a modulus? Could do. Random, yeah. Yeah, so again. That is a good idea, yeah. Yeah. I think in an ideal world, yeah, but yeah, in this case, I didn't actually check this. I've just put it into random position because they kind of start in random positions. But yeah, I know in the hint FM that first map, they do something where they're looking at the density. I think they see that if it's going slower, they know it's going to be more dense. So it's something to do with that. So yeah, but yeah, in this case, I've kept it simple, and down here, I'm checking to see if it's out of bounds. So it's just checking whether it's less than 0 or more than the width in the X direction, and similarly for the Y. And then if it is out of bounds, it basically gets a new object that's randomized. So we've got this get random point. It returns an object with X and Y properties that are randomized. So that's step 3. So now if it goes off the screen, it should reset. Sometimes there we go, it can grind to a halt as well. Yeah, there's an example. So this will go off the screen and then it starts again. So yeah, again, you can see the velocities are pretty much 0 here. So there isn't much movement here. And so this one has got stuck. It's just not moving. So that's something we'll deal with later. But yeah, you can see we're already just going into that typical kind of coding type process where we get something up and running really quickly. We're immediately running into like things we haven't thought of. Okay. Okay, next step, let's animate the particle. Okay, so that we're not having to press a key to step it through. So we use something called requestAnimationFrame. Who's used this out of interest? Yeah, okay, a lot of you. So this is a function that's built into the browser that helps you animate things. So when you call it, so here's an example here. Let's look at the one at the bottom. We pass in a function. And what happens is that function will get called when it will get called when just before it knows the screen is going to refresh. And one of the nice things about it is if the browser is busy doing lots of other things, like there's lots of calculations going on, as far as I understand it, it's not going to call your function. It's going to kind of wait until the browser is not busy anymore, and then it will call it, which is sometimes why you see kind of animations stutter a bit if there's lots of other stuff going on, but at least nothing breaks. So the idea is that, so now we've kind of wrapped, well, we've kind of still got the same step function, but now it's got this t parameter that's passed in by requestAnimationFrame. And apparently, I've only just found this out, it's actually the time that I think the previous frame ended. But don't worry about that too much. It gives you, basically, it gives you a timestamp, like the current timestamp. We also make a note of the previous timestamp. That allows us to figure out how long it's been since the previous animation frame, which then gives us a time. So it might be like it's been well, it's not going to be half a second, but say it's half a second since the previous animation frame, then that means you can then calculate how far the particle is moving. You basically multiply the velocity by that time. It's a bit like, it's analogous to if you think of miles per hour. If you're traveling at 60 miles an hour and you are traveling for 2 hours, yeah, how far have you traveled? So you multiply 2 by 60 to get 120 miles. Go on, Ali.
That makes a lot of sense. But each time you move the particle with the time limit, the field that it's sort of now in is slightly different, right? Because there are different velocities.
Yeah.
So essentially, let's do that one. Well, I think we should.
No, I think you're kind of saying it's going to be slightly inaccurate because you're kind of almost skipping. Yeah, there is going to be a slight amount, but it's close enough. It's certainly close enough for like a wind animation. But yes, I hear what you're saying. Yeah. So yeah, here this is the time delta. So this is the time since the previous animation frame. And so what we're going to do is all of this code that I haven't highlighted is pretty much the same, but now we're multiplying the velocity by the time delta. So like I say, it's a bit like if we're going at 60 miles an hour, to figure out how far we've gone, we multiply by the time we've been traveling. In the actual code, the velocity field is in pixels per second, and it could be in whatever you like, but I've defined it as pixels per second, so it's like saying it's going to travel 10 pixels in a second. The time delta will be in milliseconds, so we'll see in the code that, oh yeah, it's here. Divide by 1,000 to convert from milliseconds to seconds. So everything else is the same. We've just added this request animation frame in. So now if we look at, this is step 4. Yeah. There we go. So now, hands-free. Let's just refresh. Yeah, so it's now moving through the field quite slowly, but it's basically working. Okay, and then, so, okay, yeah, this is really interesting. Trails. So, like we've seen in the, let's go, can we get to, yeah, obviously these aren't just dots moving across the map. They're actually trails, aren't they? And it's like, okay, what's going on there? And if you look really carefully, maybe if I open this one, it might be a bit clearer. You kind of look really carefully. They're also kind of fading away towards the end of their tail. You can just about see that. So it's like, how is that effect achieved? And I can't remember if I sort of just figured it out or looked at the code. I probably just looked at the code and saw what they were doing. But it's actually, what they're doing is actually quite simple. Oy, oy, oy. Where am I going? Yeah, so what they're doing is actually, if you imagine you draw a point, and then before you draw the next point, you paint a semi-transparent rectangle over the whole canvas. So that will kind of knock back what's there. So everything that's there will get a bit fainter, and then you draw a new point. And then you do that again, and the oldest ones will get fainter and fainter. So that's all it's doing. So that means if we can do that with and just to remind you, with a canvas element, you just keep it, for this animation, we're just always painting onto it. We're never really clearing it. We're always just painting onto it all the time. But between each animation frame, we paint over the whole canvas like a semi-transparent layer, just ever so slightly opaque. So that's what we have here. We've got a function called fade canvas. So that it sets the fill style to white, but the alpha is very tiny. So if you imagine that's so that's a white rectangle that's ever so slightly opaque. Is that right? And then this is where we actually draw that rectangle. Yeah, so it's very transparent, but not completely. Yeah. So now if we add that in that step, that's the next step. So let's see what we have now. Is it step 5? No, that's not. Yes. Yeah, so we've got this now. So it's looking so much closer now. But there is a kind of, can you see that you can still see the dots? Especially with the fast ones, you can still see the dots. So what might we do? This is a bit, yeah. Draw a line. Yeah. So what we can do is now we need to store the previous, if we store for each particle, if we store the previous position as well as the new position, we can now draw a line from that previous position to the new position. So that's 5. So this is the code here. So I've somewhere. So if I comment that out, so that's where it's drawing the point. If I comment this out, back in. Now this is drawing an actual line between, yeah, let me just go up here as well. So now a particle, when we initialize a particle, it's got a previous and current position now. So now we will, where are we? Save that. I think I need to. There we go. Let's refresh. Yeah, so it's definitely quite a difference there. So we're no longer seeing those, that dotted effect. So we're getting there. Okay, this is actually the final step. So next step is to do multiple particles. So we've kind of done the fundamental work here. So now the job is to, instead of animating one particle, we want multiple particles. So now, rather than having a single object representing a particle, we're going to have an array of particles. So now when we're initializing, we loop through, we get the random point, and then we push that particle object onto the particles array. Likewise, when we're updating, we loop through the particles, and then for each particle, we do that the usual calculation where we look up the velocity and add it to the position. Similarly, when we're drawing, we loop through and draw each particle. So let's have a look. Step 6. There we go. Can I just check something? I might have. Yeah. Imagine you didn't see that. Okay. There we go. Look, it's working. But can you see that we're getting these sort of effects like here, where it's that thing we saw a bit earlier where the velocity is 0, it kind of bunches up. You might see that. we get a lot of bunching, which kind of, because it's a fixed number of particles, it then takes away from the inside. Yeah. Any idea of what we might do here? Yay! Yeah. Yeah, yeah, that's another way. I think I did, again, delve into what the others did, and yeah, I think they tend to do like a lifespan type thing. I think you saw the age variable, didn't you? No, you didn't. So actually, let's go to the whiteboard. So yeah, a way we can get around that is to add another property to each particle called age. I'll tell you why we randomize it at the beginning in a moment. And then every time we update it, we increase its age. And then if it goes above a set age, which I've called max particle age, it does the same as though it went out of bounds. It just reinitializes it. So it'll place it in a random position. Initially, when I did it, I just set age to 0. And I think I can maybe do that and see what happens. Any guesses as to what would happen? Oh, is it not reset? Looks okay, actually, doesn't it? I can't. Oops. But like you said, I think it, if I remember correctly, it kind of, they'd all reset at the same time if you set them, if you started them all at the same time. But let's just put it back to how it was. There. So I think, oh yeah, and have I, oh, no, the reason, sorry, yeah, it's because here we go. Let's try this again. It's because it wasn't actually testing the age. No, forget it. Okay. Oh, was it? Oh, yeah. Sorry. What I'll do, let's set. Oh, let's just do it. Was it? Oh, yeah. Oh, yeah. There you go. You can it sort of, yeah, you can just about see it. It kind of flickers now and then. But let's put everything back to where it should be. Sorry about the scrolling. And then, yeah, so like I say, so I mean, that is how it all works. So, I mean, and definitely have a play around with it because the repo is there. And I've just got a few little things you can try, which is quite good fun. So, like changing the number of particles. So how many particles shall we go for? No. Come on. 100,000? Come on then. Okay, yeah. Let's do 50,000. I'm wondering whether would the streaming have an effect on it? It seems a little bit slower than usual.
You could also
Yeah. So what, like the speed?
Oh, the alpha, yeah, that's good.
Yeah. So that's 10,000. So we can also change the. Yeah, I won't do that one. You can you can actually change the. So there is a. Yeah, when we initialize the velocity field, there's this parameter here that kind of sets the speed or the length of those velocities. So if we increase that, let's see, let's put it up to 1,000. Yeah, so it's still kind of so the animation itself is still at the same speed, but the points are kind of jumping much further this time, which gives the illusion that they're actually traveling a lot quicker. But yeah, this is where it is going to get less and less accurate in a sense. What else? And then maybe I'll finish with, yeah, you can change the colors, line width. There's these ones. I'll finish with these. So this is where you can, instead of having that randomized field, we can have define a field with a function. This might make you dizzy, this one. Or, yeah, I couldn't really figure out how to sort of control these. I just sort of put random functions in, but I couldn't really get a sense of what you needed to do to create a particular effect, unfortunately, but yeah. So, yeah, I think that's mostly it. Yeah, definitely.
I think we might have something on the way, but if you could give that to Peter, that'd be great. Thanks very much, Jack. Huge thanks, Peter. That was amazing. Am I in camera? Hi, camera. Thanks so much. I have questions, but does anyone else have questions first? Niall has a question. Fantastic, go for it.
Have you tried adding momentum to the particles? So they would each have their own velocities, and then it would be influenced by the vector field. Yes. So yes, but something without mass can't have momentum though, and that's what I'm. Yeah. Okay. Basically, yeah. They've got their own velocities. And then those velocities will be affected by the vector field. So it will keep on going momentum.
No, I mean, I haven't tried that. I mean, it's made me think that you could do like more of a sort of physics type system where you've got kind of gravity and so so you kind of got objects that are attracting them, which might have been kind of skips out that step of having a velocity field, I guess. But yeah, that might be a nice one to try. I don't know if you've tried that. Yes. Have you? Well, it's an idea for a talk.
I got a little one, just a playful thing. What if you, so at the moment you've got one color, black. Yeah. Can you add more than one?
Yeah, definitely. I mean, I did. Yeah. It's interesting actually, because on this, so I have done that. I'm not going to attempt to do it live, but it's really interesting because on the Earth null skull one, it kind of, without really looking closely at it, you think, oh yeah, they've colored the particles. But actually what he's done is, if we get to the
into the source.
Yeah, definitely. So here you can see the various canvas elements. So each of these, so there's lots of layers going on here. The foreground is the actual, what is, I can't remember. There's an, what's the overlay? So I'm kind of switching these off. Fast overlay. Am I hiding them? I'm trying to turn off the, let's turn off the animation. That's it. Yeah, that's what I'm trying to get to. So yeah, so what he's done is he's got a colored background, which I thought was I thought that's really effective what he's done there, because that just makes it look amazing. But the actual particles are not colored. So I thought that's a really clever thing to do.
If it was SVG, you can change the color. You just have to duplicate the first one and then overlay it over the top, maybe like a layer. Would that work, or would that be too messy?
You're probably best off using Canvas just because of the performance.
Yeah.
But you definitely can color the particles for sure. Yeah.
Okay,
Yeah.
thanks.
Mikhail, 1 second. Oh, I don't want to screech.
Thank you. So you started originally with a map of UK, and we got to an abstract grid of a grid. Did you actually trace it back to the real life data from some meteorological station and overlay the real data on a real map?
No, I've not done this. I mean, I think this is always done as a sort of as a tutorial type thing, so I've kept it simple in that respect. But yeah, it would be nice to do that. I've just found that it might not be as hard as I'm thinking. I'm sure it's not that hard, but I just haven't gone there for getting the data. It doesn't seem to be the case that you can just that the data is just there. You have to go kind of process it and get it to the format you want it.
Any data scientists here tonight? Oh, damn. That could help. It was one of those things that I was thinking, because right at the start of your talk, you mentioned that you got some information from the Met Office, but they kind of clumped things and you had to manually pick them apart, right?
Yeah.
Because all you need is the velocity, basically the wind speed and direction, like various different points in the UK, right?
Yeah.
And that's your seed data. So it looked like you already had most of it already to begin with.
Well, the data is out there. I mean, it was this here that he does actually explain how to get it, but it involved downloading sort of installing this grib to JSON script, which I saw was written in Java, and I think I just thought I'll leave it.
That's a wise idea, Peter. Yeah. Oh crap! I had a question. Yeah, thank you. Go, Brittany, go.
Did you look at trying to clear the trails at the end? I noticed that, I don't think they ever completely disappeared.
Yeah, I'm not.
How
Yeah, I don't know. It's down to that. If you remember when we draw that sort of transparent rectangle, there's that alpha value, and if it's set a bit higher so they do clear, you'll get shorter trails. I know.
If you clip it beyond a certain point, does that work, or is it
a
bit jarring? If you clip it, go for each pixel and just check the alpha, would that work? If you check the alpha, so it's
possibly. I'm not sure. I'm not sure.
Although does the alpha work? No. Probably be more the brightness.
Because you don't seem to see that effect on this one. So I haven't quite got to the bottom of that. There might be a way, and it might be that just drawing a semi-transparent rectangle is maybe a bit of a crude way of doing that. I'm not sure. But if anyone has any ideas.
That's okay.
Off of the back of that, I'm visualizing that you have an infinite sandwich of Is that what it essentially is? And then does it clear itself at so many?
No.
Because I'm thinking computationally as well. Does that affect the processor speed or anything? Or
Don't think so, because it's just a grid of pixel of it's basically a grid of colors in effect, and that's always what it is. And so when it draws the transparent rectangle, it's looking at what's currently there and then making it whatever 99% of that, and then draws. So yeah, there's no sense of it kind of being additive over time.
Thanks.
Sorry, Dave. Dave was next. As I go to Dave, I just want to say that web tech requires a lot of analogy, sometimes explain things, and I think Infinite Sandwich is one of my favorite.
I've got a couple of ideas that I just wanted to share for the video.
Yeah.
So one is, you see this little map here where there's I guess this is real weather data, right? There's a little sort of spinny thing going on the right there. There's this sort of storm going on. If you took when you generate your vector field, when you actually put your vectors in, rather than putting the ones that sort of point uphill, maybe if you turn them all 90 degrees to the left, you might end up with some eddies kind of going on, which might make it look a bit wind-like. It's just an idea.
Yeah.
The other thing is, when you're saying you're having difficulty generating fields at the end, you got that big sinusoidal one that's very impressive. There's a really cool algorithm called a Perlin noise field. So have you used that before?
Yeah, okay.
So it's basically, for anyone who doesn't know, it's just it generates sort of things that look like clouds. And then if you just, it's not the sort of code you want to write, it's horrible, but you can find the code and just use it, and then you get a nice little cloud for your little vectors. Okay. And then that might look pretty good as well.
Yeah, that's a nice idea.
There'll be an NPM package for sure.
I do have a solution for the fading out, not fully, but it's a little bit more expensive computationally. Just record each of the previous positions and then draw a white rectangle, completely opaque.
Okay.
And then draw each of those previous positions with a level of transparency on it. Again, it's going to be quite a lot more expensive, but yeah.
Interesting. Yeah. So you kind of draw in the whole trail each time. Yeah.
So we should probably start wrapping up soon. I wanted, since I've got the microphone, I'm just going to use it. This was an amazing talk. Thank you so much, Peter. I think one of my favorite blogs is by a guy called, and I'm going to butcher his name now, Bartosz Chinovsky, and I'm wondering if you've come across him at all. Okay, damn, I'm going to have to find this, Google this. Do you mind if I sort of just Google it quickly while I'm showing you? Because this seems, to me, this was almost like a real life talk from one of my favorite blogs. There he is. Have a look at some of this stuff. No, damn, Chianovsky. Damn, I got it wrong. Okay, never mind. I'll find it for you and show you later. But he is an incredible pedagogue and explainer of this stuff, and he handcrafts all of his own animations as well. And a lot of this stuff really reminded me of this. So yeah, highly recommended. Any last questions? One last question from someone. Well, yeah, that was Charlie's got a question, so you go for your observation.
Short one. I had a problem with meteorological stations having numbers to them, and you have a sparse array that are provided by the Met Office, and a couple of lines of, I think it's NumPy, there's actually an interpolation function that will take a sparse grid and just give you a nice clean.
Yeah, okay, that would do it. Interesting.
Nice. And no Java.
Okay. Python though.
yeah, better than Java.
So I'm coming at this from the perspective of somebody who knows little to know about coding, but this is such a cool, like the visualizations are so cool. Yeah, thank you. Like that's, in fact, let me put that on the live stream. That's exactly what I'm talking about. And I come at this from a background of like music and creativity, and something I love is going to a gig and seeing like a really, really great light show or like a really great kind of visual element to complement the music that you're hearing. And I was wondering if is there something like kind of in this already that exists, or is it something that could be done where one could be taking the code that you're doing here and kind of doing and making changes along to a live show over the course of like, you know, an hour or however long? How would you do it?
Yeah, maybe. I mean, I guess if you can get like to sort of be driven by the music or the sound. Yeah, potentially.
Or driven by whoever's driving.
Oh, I see.
You know.
Yeah, I mean, I was wondering about. Well, yeah, I don't know. I guess you could. I think, to be honest, there's probably better tools out there that are a bit more interactive, if you know what I mean. I think I can't remember the name, but I think there are kind of tools that are a bit more interactive for doing kind of graphics and animations and stuff, and sort of generative type animations. But yeah, I mean, potentially you could. I never experimented with this, but it might be quite interesting to make the velocity field change over time as well, which I didn't play around with.
Could you do it with the timestamps?
Yeah, I would have. Yeah, you could have them like rotating or something.
Yeah. Or similar to timestamps is beats. You know, you could
there you go.
have because these, like as you've demonstrated so clearly here, each of the seed points is a field, right? And so you could potentially change the fields, the seed points in tandem with the beats of the music.
Yeah,
I reckon, and yeah, I think it would look sick.
100%. And I mean, because I noticed. So, for example, exactly as you've done there, do you have to refresh as you go to like make these changes go live, or is there a way that you could kind of, you know, transition from, I think about it in production terms of like a scene, from the scene that we were in before to the scene that we're in now, and make it more gradual than just refreshing?
Yeah. I mean, it would need further coding to kind of add that sort of interactivity to it. I didn't actually open this. I have it on a code pen, but it's a slightly different version. I don't know if it is. Let's see if I can get to it. Yeah, so I did make a code pen where you could actually, here it is. Like I say, the algorithm is basically the same, but there's just a few differences because I kind of changed things slightly to make it easier to sort of explain. But yeah, with this one, you can actually move the seeds around and actually define your own. Oh, sorry. Yeah, we'll define new seeds. Sorry.
Just pull this one out of the end, Peter.
There we are. Yeah, so you can move them around. There we go. Or add new seeds. Oops. I think.
Can you change the color?
You can. There we are. Yeah, you can. No, but.
Are you free throughout the Brighton Fringe?
Yeah, and so you got speed as well. Number of particles. So you just have a few. Have I got width? Yeah.
That's awesome.
Yeah, so you kind of potentially add anything to that. But yeah, but like I said, I think there are tools out there that are maybe a bit more suited to those kind of visuals.
No one's giving an async talk about them though, are they?
True say. Jake, one of our organisers, has just said on a YouTube comment, he wants to make a suggestion that you could have the velocity field be powered by live webcam footage and have it be interactive.
Nice. Well, there you go.
There you
could.
Wow. Somebody else says Hydra is JS for music plus visuals.
Ah,
if anyone knows what Hydra is.
No.
I'm going to find out.
Yeah. I do from the Marvel movies, but I think it's different. Okay. Fantastic. I think that's it. Thank you so much, everyone, for coming, and what a wonderful talk, Peter. Thank you so much. So another huge thanks to Silicon Brighton and to Runway East for hosting us. At the end of tonight, we're going to, if anyone could help sort of move furniture and stuff, that'd be great, greatly appreciated. But we're going to head round to Unbarred, which is just sort of first right, and then at the end there. So please come and join us. But please put your hands together for a huge round of applause. Thank you, Peter.